Okay, so this is hour 2 for September 8th, and we're going to be talking about uh, electric potential. Okay, so the word potential is something you've probably seen in physics before. You've probably heard about it in other things too. You know, you can say that some student has a lot of potential to do well in math or physics, or maybe another student has the potential to do really well with writing. You could say that a basketball player is like has the potential to become great or something like that, right? Potential is about something that hasn't happened yet, right? It's about something could happen. There's a potential for it to happen. There's a possibility for it to happen. That's what that word means. And we want to relate that idea to electricity. And we want to use it to describe why it is that charges may flow from one region to another region, from a high potential region to a low potential region, or a high energy state to a low energy state. Okay, potential is all about connecting energy to electricity and providing new ways to talk about things other than just electric fields. Okay, so in order to understand this, we are going to start off by talking about work. We're going to connect work to what's called electric potential energy, and then we're going to connect that to electric potential. That's kind of our plan here. Is to start with the concept of work being done, connect that to electric potential energy, and then get electric potential. Now, there's a distinction between these two things, and hopefully it'll be clear to you what it is here in a second. So how do we do this? Suppose that I have an electric field. So I tell you in some region of space we've got an electric field. Let's draw some electric field lines. We've got some field lines that go like this. Why is it doing that? Copy, paste, 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 paste. So I've got some region of space, and I tell you that I have an electric field in this region of space, and I tell you it has some value, and maybe that value changes over the region, or maybe it doesn't. Not really important, but I give you these field lines right here, right? And then within this region of space, I take a positive charge. So I take some charge right here, and we're just going to call that charge Q sub 0 for whatever reason. Okay, but it's positive, right? And then we say, well, we know that there's a force acting on this charge. Can you guys type in the chat? What would the force acting on this charge be? What direction would it point? I give you an electric field, I give you a static point charge. It points to the right, yeah? That's right. And what's the value of that force? What's the value of that force? Force is a vector. It's Q times E, exactly. You take the charge, which is Q naught, and you multiply by the electric field. And the force is a vector, the electric field is a vector too. Right? Now let's say that our charge moves through some displacement. Okay, so let's say it moves from some point. Maybe we call this point right here point A. And let's say that it moves over to here so this is point A, right where it starts. And let's say that it moves over here to some point that we call B. Okay, it undergoes that path from A. Oh, no, I knew that was going to happen. I'm going to have to just draw with an arrow because I can't draw straight on my lap. So it moves that way through some displacement, right? And it's a displacement, so I don't know, let's call it delta S or something like that. Or I guess we do delta X, I don't know. Let's do delta S. And it's going to be a vector. Okay, and let's say that the magnitude of that vector, so A to B is a path, let's just say something like that. The path is equal to delta S, and the length of that path is D. Okay, and we want to calculate what is the work done by the electric field. We'll say more specifically the electric force. How do you calculate work done if the force is constant? How do I find the work that's done? Just the force times the distance, basically, right? And if I want to write that in a more specific way, we could use the dot product and say that it's basically just that force dot product with the displacement vector. So dot product with delta S. But as long as the particle moves along a path that's parallel to the force, this simplifies greatly to just become Q naught, that's the force, times E, multiplied by the distance d. That's the work done. But there's something that we learn in Physics 1A, or you may or may not have learned this. Certainly if you took my class you did, but you almost certainly covered this topic at some point. And it says, if I know the work that's done by, let's say, a conservative force, then there's a connection between the work that's done and the change in potential energy due to that force. And I'll tell you right now that the electric field is a conservative field. The electric force is a conservative force. That means it acts like gravity. It means it's path independent. We'll prove that later, but just trust me for now that that's true. We'll prove a little bit down here that it's true, that it's path independent. It doesn't matter how you go from A to B, you're always going to get the same answer, okay? You could travel along a curvy path, a straight path. Doesn't matter. You're going to get the same answer, okay? And there's a connection between the work done and the change in potential energy. And this isn't exactly right. There's something missing from this equation. What's missing from this equation? Work done by a conservative force, how is it connected to change in potential energy? No. Not kinetic energy. We will connect this to kinetic energy. We just want to connect the work done by the force to the change in potential energy of the system. Negative delta U. Yeah, that's right. There should be a negative sign here. When a force like gravity does work, it has the effect of decreasing potential energy if the work done is positive. If the work done is negative, you increase potential energy. It's a negative connection. Simple way to think about this. I take a ball, okay, and I place it near the surface of the Earth. The ball has a mass m, right? And I think about what the force of gravity does to my ball as I move it. We know that the force of gravity acts down in this direction, right? So what happens if the ball moves down? What happens to the change in potential energy of the ball? If I move the ball downwards, does the potential energy increase or decrease? Decrease, right? It goes down, right? What's the sign of the work done by gravity if I make the object move from here down to here? So it moves downwards from like A to B. Work done by gravity is what? Positive or negative? It's positive, right? And at the same time, delta U, with respect to gravity, the change in potential energy to gravity is negative, right? Does everyone follow that idea there? Do you remember potential energy well enough to understand that potential energy is high when an object's really far above the surface and it gets low when the object gets close to the surface? Because after all, the potential energy due to gravity is just mgh, right? Or mgy. So if the ball moves upwards, if it goes from A to B like this, well, it's probably because you took it on the internet. I bet, Ash, is probably part of it. Not your fault, it's just that we didn't really get to actually have a class. Anyway, whatever. If the ball goes from A to B the other direction, what happens here? So in this scenario, you go from A to B. Is the work done by gravity positive or negative? Work is negative, delta U is positive. Okay, that's what this equation says right there. That's what it says. It says that if an object moves down in a gravitational field, it loses gravitational energy because gravity does work on it. If an object moves up in a gravitational field, it gains potential energy, but gravity does negative work, and you need to put energy in the system to force it to lift up there. Objects tend to move, and this is something that's really important. I'm going to say this. You guys would agree with the statement that if I have an object and I put it on top of a hill, and there's a way for it to roll down the hill, it's going to roll down the hill, right? Objects tend to move from higher elevations to lower elevations, right? Everyone agree with that statement? I take a ball, and I release it from rest somewhere. It's going to fall downwards, basically, right? Things tend to move from high elevation to low elevation, okay? And I want you to remember that idea of elevation, okay? Because elevation is the best synonym for what electric potential is going to be. If I wanted to tell you what electric potential is for gravity, I want to say gravitational potential, it would just be elevation that would determine that, okay? So I want you to just remember that kind of analogy. It's not even an analogy, it's almost exact. So, okay. We've got this connection here. Work is related to the negative of the change of potential energy. So let's just apply the exact same thing to what we wrote right here. So we say that the work done is equal to Q naught ED, then the change in potential energy due to the electric field, let's say, would be equal to the negative of this, right? Negative Q naught times E times D. All right? That's what it would be. That's what the change of potential energy in this particular case would be. So the next thing that we can do is say, okay, well, what if we were to divide the Q naught over to the left-hand side over here? So we write it as change of potential energy divided by Q is equal to negative E. And now instead of this distance D, which is going to be a useful way to think about this, let's just replace this with delta S. Doesn't really change anything. After all, the magnitude of delta S, we're calling it some distance D. But now what we'll do is we're going to define electric potential. We're going to use the symbol V to be equal to U, the potential energy at some point, divided by the charge. I should have left the Q naught in here. So we're going to define electric potential. This is electric potential. To be the energy divided by the charge. So it's basically, well, it's that. It's the energy per unit charge. It's the energy per unit charge. That's what it is. That's what electric potential is. Electric potential energy is this thing. So this is what we call electric potential energy. When you drop the word energy, you just get electric potential. That's this one. So try not to confuse these too much. But given that, I can now define that the change of potential, the change in electric potential, in the scenario that we put right here, is going to be equal to negative E times delta S. The unit for this, 1 volt, capital V, is equal to 1, you can see from here, energy is measured in joules, and charge is measured in coulombs. That's a volt. 1 volt. And that is what electric potential is. That's basically what electric potential is. We're going to do some problems, we're going to look at some scenarios, but that's basically it. It's the amount of joules per coulomb that you have in a region of space. So in a region of space, you may have 10 joules per coulomb, or 10 volts. And in another region of space, you may have, like, 0 volts, okay? What's an example of that? Well, a common example we're going to see show up a lot is we're going to have a positive plate of charge, we're going to have a negative plate of charge, and we're going to say that, I don't know, maybe this plate on the left is at 10 volts, the plate on the right might be at 0 volts, so that delta V between the two plates would be equal to 10. The positive plate's at a higher electric potential, the negative plate's at a lower electric potential, and if I am to come in here and put a charge between the plates, like let's say a positive charge, it's going to tend to move from high potential down to low potential. Does that make sense? This positive charge would move from high potential down to low potential given enough time, if released from rest in this system right here. And that's a general statement that we can make. Positive charges from high potential, high voltage, to low voltage. And again, if you want to replace this with gravity, instead of 10 volts, you make it 10 meters and 0 meters, and say massive objects tend to move from high elevation to low elevation. That's what voltage represents. It's like elevation, effectively. I'll stop for a second. Do you guys have any questions so far? The opposite of this is true as well. Negative charges are going to tend to move from low potential up to high potential. Why does it want to move from high to low? Part of the reason is that the electric field within this region of space is always going to point from the positive side to the negative side. So this arrangement basically creates an electric field in this region of space that looks like this. So if the electric field points from positive to negative, then the positive charge is going to tend to move along those field lines. So going from 10 down to 0 tells us something about the electric field. The electric field lines point from high potential to... You could replace positive charges here. I could also say that electric field lines point from high potential to low potential as well. Does that answer your question, Ash? How do I know that? Well, let me add something to this picture here. What if I tell you that delta S between here and here is equal to, let's say, 2 centimeters? This is basically the problem we're about to do here, but we might as well just do it with these numbers. What does this equation right here say? This equation says that electric fields is basically equal to the negative of the change in potential divided by the change in distance. Right? So what would that be in this case? So what's the actual change in potential? Well, we got to pick 2 points. If I want to just describe a change, I need to pick 2 points, right? So let's make our first point here to be A, and our second point here to be B. And this is the path. Let's say that the object is moving along. There's no object necessarily here either. We're just looking at a path from A to B, right? So we would say now that our electric field needs to be the voltage at point B minus the voltage at point A, all divided by the distance between the 2 points, which we have down here is written as 2 centimeters. Okay, so 2 divided by 2 centimeters. So what's this equal to then? Well, the potential at point B is 0, so we end up getting negative 0 volts minus the voltage at A is 10 volts, right? So 10 volts here. And then we divide that by our 2 centimeters. But of course we need to convert that to meters. So 0.02 meters. And then we get our answer. Negative 0 minus 10 is negative negative, so you get a positive 10. 10 divided by 0.02 is going to be like 500? I probably did that wrong. Is that right? Yeah, 500, okay. So that's our electric field. And its units, it looks like there's kind of like a new unit here, right? Volts per meter. It turns out that 1 volt divided by a meter is equivalent to 1 newton divided by coulombs. So up till now, we've been saying that the electric fields had units, like we wanted to talk about the units of the electric field. It would have the units of, volts per meter now, which is the same thing as newtons per coulomb. You can work out for yourself that if a volt is a joule per coulomb, it's only one step to prove that this is true. But very commonly, you're going to see volt per meter is like basically your new measurement of what the electric field is. Okay. Now, this is kind of a nice relationship right here if you think about it. This tells you that, think about what this says. It says the rate at which the voltage changes with respect to distance tells you the size of the electric field. So if, for example, this plate was 20 volts and the other plate was 0 volts, the change in the potential would be much greater within this region of space. Bigger change, bigger field, right? And it's really about just the rate at which the voltage changes per unit distance that you move. This is actually the way we measure electric fields in the classroom. The first lab that we would be doing in this class, you'd be measuring voltages at different points in a liquid, and you'd be finding the electric field by saying, okay, if I know this one's 8 volts and I know this one is, let's say, like 5 volts here or something like that, if I know the distance between these 2 points, I do 5 minus 8, that's 3. If I know the distance between the points, I can figure out what the electric field in this region of space is. And for a field that's produced like this, you're going to get the same answer no matter what 2 points you pick, right? It's the change in voltage divided by the change in... yeah, the lab that we would have done in class, what we do is basically, you have this big tray, and in the tray what you do is you put a metal bar in one position, you put another metal bar over here, and you connect the bars with a wire up to a voltage source. What's a voltage source? That's something we have to talk about, I guess. You connect them up to a voltage source. Now, the voltage source we use in the class is what's called an alternating voltage source. Kind of like similar to the voltage that comes out of the wall. But the effect is that one of these plates ends up being at about like 6 volts. The other plate ends up being about 0 volts, and you do that by tuning the machine, okay? And then you literally just take something called a voltmeter, okay? And a voltmeter is literally just this device where you have like a black little piece of metal that you plug in and a red piece of metal that you plug in, okay? And the way that you do it in the lab actually is you basically take the black... Oh my god, why must it be like this? You take the black one, you connect it over here to the... Here, so you got your black electrode, and you connect it up to here. I probably shouldn't be, this is going to be not good. And then you probe the value at other points. And so then here you have this thing called a voltmeter. The symbol for the voltmeter is kind of like this. It's got these little electrodes that come out of it, and you can use it to measure voltages. And you'd basically just measure the voltage difference. And so what you'd find is right in the middle here, you're going to get a point where it reads 3 volts. You'll move this red thing to a different point, and you get like 4 volts or whatever. And you use this whole system to basically calculate it out. Your question is done in a liquid. The whole system is filled with liquid water. And it's filled with water because water can tend to be kind of conductive, so you can actually read out a voltage, whereas when it's in air, it's very difficult to read it out. So yeah, it's done in a liquid. Specifically water. A very thin layer of water, basically. You do some calculations with Gauss's law, and you end up figuring out the number of charges per unit meter squared on this thing right here. You have to use AC current, I believe, because otherwise... what's the reason for using AC? I don't immediately remember why. I think if you use DC current that you don't really get much of a readout inside the liquid. I don't immediately know the reason for the AC current for this lab. But, yeah. Yeah, off the top of my head, I don't remember the reason why. Okay, I'm getting, what is, AC is alternating current. See, I'm already introducing words that I shouldn't be introducing to describe a lab that we would do before we even knew what alternating current is. We'll talk about alternating current later. We gotta talk about current first. Right, let's do a problem. Oh, we never did this problem. Maybe we'll do this one on Thursday. I know you have at least one homework problem like this. That's okay. Let me take some of these pictures that I have here to, like, tell you guys some things. So, this is a picture of kind of a better drawing of what I was just describing. So, imagine you have an electric field in a region of space, represented by these straight orange lines right here, right? That's our electric field. We're comparing this to a gravitational field, represented by the purple lines right here. To compare the two of them, we need to have a positive charge on the left-hand side to feel a force from the electric field. And on the right-hand side, we need to have a massive object to feel a force from a gravitational field. But then if you read what it says right here, when a positive test charge moves from point A to point B, the electric potential energy of the charged field system decreases. That's what you're saying. As you move from high potential to low potential, the energy decreases. Same thing happens when an object moves from point A to point B in a gravitational field. So that's kind of just a nice image to describe the connection between those two things. So what about a system like this? So what if we want to look at a system where we don't move in such simple straight lines like this one here? How does that end up working out? So let's say that we want to describe the work done by the electric field, yeah, we'll use the dot product. So let's say that we want to look at what happens when an object moves between point A and point B, and we want to compare that between what happens when an object moves from point A to point C. Okay? So let's figure out what the electric potential is in both of these cases. Okay? So really what we want to know here is what is the potential difference between points A and B. So I'm going to call that the delta V from A to B. We want to calculate also the change of potential. Okay, and I'll try to remember to do this. I'll try to put these lines here to represent that it's a capital V. What else? We want to do from A to C. And then finally, we'll do delta V from C to B. Okay, those are the three things we want to calculate. What are these all equal to? And in the previous part, what we had said was that delta V was basically equal to the electric field dot product with the displacement. And then there's a negative sign in front of it, right? All right. A to B. Let's do this one first. This is the one that's a little bit different. So to go from A to B, what we've got is... we have negative electric field. The electric field in this region of space is going to be uniform, so it's the same value everywhere. It's just some number. It could be like 20 volts per meter or something like that. We would have negative. You have the electric field. You have to multiply by delta S. And then we have to multiply by the angle between the two of them. Now, in this case, delta S is just represented by the variable S, right? So we're going to get rid of the delta. And we're just going to say it's basically going to just be E times S. Oh, no. It's going to be E times S, and then we have to multiply by the cosine of the angle between the two of them, cosine theta. But then we look at the picture. What's S cosine theta equal to in this triangle right here? Why I was able to remove the delta? So this just means, so when I do the dot product, right? When I do the dot product, the delta just represents like the change in position, like from here to here. And it's just being called S, so it's just like the length of the line. There'd be nothing wrong with leaving delta S in here, I guess. As long as we recognize that it basically represents, like after you do the dot product, it represents just the length is the reason I pulled it off, basically. It's just the length at this point. But then as you said, S cosine theta right there, that piece, if you look at the picture, is equal to D, right? So you end up getting negative E times D. That's our answer, right? Delta V between points A and B is negative ED. Point A is at a higher potential than point B, right? All right. What about E to C? Well, we already did this. We already looked at a problem before where we went in a straight line. So that if you go from A to C right here, you immediately get the E dot delta S just becomes E times D, right? So you get E times D. Same answer. So the potential difference between the 2 points, A and B or A and C, they have the same potential difference, basically. Right? What about if you go from C to B? Well, if I go along a path in this direction, if that's my delta S, so to speak, then at every point on that path, the electric field's at a right angle. So now what happens if I want to do delta V along the line from C to B? What we end up getting is E times whatever the length of this side would be. It'd be like, S times the sine of theta or something like that. Let's just call it, let's say the magnitude is equal to, I don't know, Y or something like that. You'd get E times Y, but then you have to multiply by the cosine of 90 degrees. And that is 0. So delta V from C to B is equal to 0. Well, that's interesting. If this is 0, that means that any change in position along any line that's perpendicular to the field lines, right? So if I came in here and I draw a line, I want to draw a line like this. If I draw a line that is perpendicular to the field lines, oh no. Why do I have to keep clicking this every time? That's really obnoxious. So if I take any line here that's perpendicular to the field lines, like B and C like this, the electric potential is the same along every single point along those lines. So we could say that, well, he says right here at the bottom, points B and C are at the same potential, right? And what that means is that these lines, along lines like this that I've drawn in here, where the electric field is perpendicular at every single point, the electric potential along all those lines is the same. So these blue lines have a name. They're called equipotentials. Oops. Equipotential lines. Because the electric, or the electric field would do no work on a particle if it moved along one of these lines like this. It's only motion parallel to the field that the electric field does work with. So we call them equipotential. I did not spell it right. That's not spelled right there. Wait. Maybe it is spelled right. I'm crazy. It's a line where there's no change in potential energy. There is potential energy at that point, though. But there's no change in potential energy as you move along the lines, moving from one point to the next to the next. So it doesn't take any work to move a particle along the surface. So what's the what would be the equivalent to a line of equipotential for a gravitational field? What's a line that I could draw on a gravitational field? A height map, but then specifically, what do you mean? What would an equipotential line look like on a hill? You have to have constant elevation, basically, right? So this would represent, like a line like this in a gravitational field that has the same elevation represents an equipotential line. And we can take that to an even simpler statement. If I have a table, right? If I have a flat table, that doesn't look flat, and I have a ball on that table, the ball is basically going to sit still, right? There's no, because the surface of the table has the same potential energy all across it, right? The same elevation. So such an object, it doesn't, if the table's frictionless, it takes no work to move the ball to the right or to move the ball to the left, right? Assuming it's frictionless, right? If you introduce friction, that's a different story. But okay, you also mentioned height maps, Ash, and that's definitely a good thing to mention here because equipotential lines, technically in the real world, are going to become surfaces. And an equipotential surface is just a surface along which the electric potential is the same. And we have, okay, this is really obnoxious. I have to literally click that to get this. That is just, so I pulled a picture of one of these. I don't know if this is something you guys have all seen. I think I find it common that people haven't seen these things before. So this right here is what we call a topographical map. Have you guys heard of topographical maps before? Right, this one, I just pulled this one off Wikipedia. This one also has shading. A topographical map is something that basically shows you not just locations, like here's some place called Lower Village and some place called Stowe or whatever. This is a map, right? But it also shows you the elevations of the land. So there's a hill over here called Cacti Hill or something, I don't know. And you see how there's these lines? There's a line right there, there's a line right there, there's little circles and stuff like this. Every single one of those represents a different elevation. So this line right here represents 800, this line right here represents 900, and we can count the number of lines in between. So this is 800, there's 1, 2, 3, 4 lines in between. So this line that's right next to the 800 represents probably 820 feet. And then 840 feet, 860 feet, 880 feet, and then 900 feet right here. The distance between the lines, what does that tell you? The fact that these two lines here are really far apart compared to, like, let's say right here where the lines are really close together, what does that tell you? It tells you change in height, but what does it tell you? What's the difference? Evaluate between like these 2 points that are far apart versus these 2 points that are close together. It tells you how fast it changes in height. What does that tell you about the terrain then? Steepness. There you go. Perfect. That tells you how steep it is. The slope, Ty. That's right, exactly. The closer together the lines are, the steeper the slope is, right? The farther apart they are, the more gradual it is. And in regions like this here, this is like a big flat area, right? Big flat area here, big flat area here. Obviously some flat areas next to the river, but then there's like a steep slope next to the river here. Yeah, so, and then you see this region right here is really steep, right? That's like a very sheer face because the lines are literally super close together, okay? So just let's take this back to what I said before. The size of the electric fields is related to the change in potentials over a region, right? The size of the gravitational field is going to be related to change in elevation over a region, right? So if you have a region where the equipotential lines are close together, it's going to have very high electric fields. So what does that look like? So this thing right here, when you have a uniform electric field, this might be 8 volts, this might be 7 volts, and you would have these lines perfectly spaced out from each other. So if I take these two, I can't control click both of these, that's whatever. If I want to put in a 9 volt line, I would need to make sure it's exactly the same distance apart as the other two. So this right here might be my 9 volt line. 9 volt, 8 volt, 7 volts, they need to be equally spaced. So if this one is 1 centimeter away from this one, the next one has to be 1 centimeter away from the other one. It's a uniform field. A uniform field is like a gradual slope, right? It's a flat slope, right? But there's going to be regions in space where you don't have a uniform change, right? What's an example of that? So a point charge would be a perfect example where you're not going to get these nice, straight equipotential lines, right? We'll talk about a point charge next, but I'll just tell you, just as a hint, is what's going to happen. Positive charge, right here, let's say, it has electric field, right? At what area is the electric field the strongest? Is it close to it or far away? Close to it, right? So that means if I want to draw equipotentials around this object, the equipotentials that are near the charge are going to have to be close together. Then as I go farther away, the distance between them might get smaller. And we'll talk about what the values might be. Like the first one might be 10 volts, the next one might be 5, and this one might be 2, and this one might be whatever. But the place where the R is the smallest. So this would kind of look like the equipotentials around a point charge. We'll talk more about that here in a little bit. Okay, so I have to click this, and now I've got to go grab this problem. There's several problems I want to do here. Basically, we just already did this problem, so we're not going to worry about it. We're not going to do that one. We will do this one, though. But I want to do this part first, though. So this is a quick quiz about equipotentials, just to give you an idea of like what they are. And maybe we haven't said enough yet to where this is answerable. But look at this question. We've got equipotential surfaces, okay? One that's 6 volts, 7 volts, 8 volts, 9 volts, and then some points. A and B are both on the 9 volt surface. It looks like E is on the 7 volt surface, so is C, and then D is on the 6 volt surface. So it says, the labeled points in the figure are on a series of equipotential surfaces associated with an electric field. Rank, from greatest to least, the work done by the electric field on a positively charged particle that moves from A to B. We're going to rank that compared to B to C, C to D, and then D to E. So rank them, and if it's negative, that would be the smallest amount, right? If it's positive... Oh, I have a question about what we just did. I'm sorry, let me look at that question. Your question here, why is it negative ED? Oh, okay. I kind of just said what we just did of it. I should have said, as I'm moving from point A to point C, the electric field points to the right. Our definition of what delta V is you do the electric field dot product with the displacement. So the path that we would take, right? The path that we would take here would be pointing along this direction here. That would be the path from A to C. The length of the path is D. So this would become D. The size of the electric field is uniform in this region. and we'd multiply by the cosine of the angle between the path and the field. The path points to the right, the field points to the right. That means the angle between the two of them is 0, and we have this negative sign here. That's the answer as to why. Okay, so let's go back to the question again. So again, what I want you to do is you want to rank A to B in terms of work done by the field, B to C in terms of work done by the field, C to D, and D to E. And if it's negative, you're going to make it the smallest, and if it's positive, it'll be the biggest, right? So just rank from 1 to 4 these paths, and I'll give you guys some time to think about that. Hopefully the question makes sense. I'll write down some equations here too. The work done is equal to basically, what is it, negative Q times delta V. So you could think about this for part A as being the work done would be equal to negative Q times, it's a positively charged particle, right? Yeah, positively charged. So this is a positive. You do the change of potential, so you go final minus initial. So if you're going from A to B, it would be VB minus VA, right? What's this one going to be equal to, by the way? If A and B are both on the 9-volt equipotential, what would this one be? 0, yeah. Okay. Can you delete your response, Ty? You're always way too fast with these things. So what I want you guys to do is to just think about it, take a few minutes, and then I will ask for your answers. Is that okay? Please, Ty, just delete your response. I'm going to delete it. And in the future, I've mentioned this before, please let other students have at least 10 seconds to think about something before you answer. You can't just be instantly answering questions. I know that it might be easy for you, but that doesn't... Just if you know, just like let them try. One of the biggest parts of education is people need to have the chance to think about things. I'm going to shut up. You guys think about this and see if you can't rank these. He just studied. He read before he came to class. That's the reason why, is what I would guess. Not to say that other people didn't, just, probably just read a bunch. Give you guys like 2 minutes, I think. Okay, it's been 2 minutes. You guys can type your answers in now if you want to. C, C, D, A, B, D, E. I believe that's right. Because B to C is changed to 2 joules. C to D is a change of 1 joule. D to E would be -1, and we already saw AB was 0. B to C, C to D. Yeah, you're saying the same thing. Okay. Does anyone have any questions about why that's the right answer? So let's go through each one of these. So look up here and see that basically the biggest thing to look at is negative V minus V, basically, right? We already said A to B was 0. Going from B to C, and the units on this would have to be joules. Let's assume, just for simplicity, let's let the charge be equal to 1 coulomb. That way we can just automatically. When we go from B to C, so from B to C what you're getting is B is 9 volts and C is 7 volts. So for B to C you'd be doing Q times, and there's a negative sign, it's final minus initial, so you go C minus B. So that's going to be -1 coulomb times VC, which is, it's on the 7 volt surface right here. And then minus VB, which is on the 9 volt surface. So you end up getting negative times 7 minus 2, or 7 minus 9, which is -2 times negative, you get positive 2 joules. Coulombs times volts gives you joules. C to D, we can kind of skip the math now if you understand the idea. Going from C to V, you're going from 7 to 6. So -6 minus 7 ends up being 1. So this would be like positive 1 joule that the electric field would do work with. And then D to E, you're going from 6 to 7. So 7 minus 6 is 1, but there's a negative sign. So this one would be -1 joule. And since what this means is if it's negative, it means that you need to put work in to actually make it move that way, right? A positively charged object might naturally move from C to D. It might naturally move from A to B. But in order to force it to move from D to E, that's like pushing something uphill, basically, right? Does that make sense? Anyone have any questions? Okay, so hopefully you have some understanding what voltage is. We can connect this back to the question that Miaris had brought up in the last topic, where he said, why is it that birds can stand on these high voltage lines? So I think I can answer that in a better way now. So if you have one of these lines, so let's say you've got a pole, let's say you've got a pole here and you've got a pole here, and connected between those lines is your power lines. There's usually 2 of them, right? Like, I don't know if I can properly draw this, but there'd be a second one back here too. So he was saying that these lines are actually exposed to the air, so it's just open metal, and the amount of voltage in one of these lines, I believe, is on, if it's going from like city to city, for example, the voltage ends up being on the order of like 10,000 volts, I want to say. But the thing is that the surface, the conductor itself, is an equipotential surface. This is one of the things you mentioned, Ash. And it's connected to the idea that if you have a conducting wire, so let's just look at a wire real quick and talk about what's going on with it. You can have it so that this point over here is 1,000 volts, or 10,000 volts, and this point over here is 10,000 volts. So that basically there's no potential difference when the bird sits here. So if the bird's feet are here and here, and then here's the bird. Oh man, I'm not going to draw a very good bird here. So there's our bird. If this foot is at 10,000 volts and this foot's at 10,000 volts, well then it's not going to feel anything going through it. I think that's the idea. However, if the bird were to put 1 foot here and 1 foot on the pole, you might get electrocuted, right? That's what you're saying? Does that sound right, Miaris? What you read in that article? Because the pole's connected to the ground, and the ground, okay, so the ground itself, we should talk about what ground means. The Earth is basically like a kind of an infinite receiver and giver of electric charges. If it's ground, I think we usually call ground 0 volts or something like that. Or maybe even negative volts, I don't know. But I think we say it's 0, so even if it was negative 10,000 volts, you could still lose or gain energy from the ground. So if 1 foot touched the pole, but see, then if the pole's made of wood, I feel like if the pole's made of wood, you might be okay, but maybe I'm wrong. If he touches any metal on the pole, he's going to be in trouble, though. Why is the charge equivalent on both sides? I didn't say anything about the charge. There's 100% charges that are flowing through here. This is something we haven't talked about yet, but there's a flow of charges in the system. All the charges will be flowing with some current, with some very, very low amount of current, basically. Okay, alright, so we need to take a break. It's already 8:03, so we'll take a break until 8:15, and we'll come back and finish things up. But I'll wait a second and see if you guys have questions or comments. Maybe I was just typing something, so I'll give them a second to finish that. I'll stop the recording for now, though.